everyone, and welcome to the 12th week of the course Advanced Structural Analysis. We have almost covered the 11 weeks of the intense course in which we discussed the basic methods of the structural analysis from the manual calculation point of view. Then we introduced the basic introduction to the computer implementation and implemented the regular stiffness approach for the problems of the beams, frame, the trusses within both the space and the plane structure form. And later on we started with the discussions on the nonlinearity in the system, and our focus was somewhere on the geometrical nonlinearity at the beginning. And with the last week we started brief discussions on the material nonlinearity in the given system. In the today's session we will try to cover the basic aspects of the material nonlinearity and try to understand that how it can be included in the regular problems of the structural analysis. The content which we will be covering in this session includes the general tangent modulus of the nonlinear material relationship, the plastic strain increment which becomes one important aspect of the nonlinear analysis, and then the general uniaxial stress strain increment relations of the given system. Though the expressions are defined with the uniaxial cases, but of course the utility of the similar form or the derivations is equally applicable to the multi-axial loading in the given system also. Now, coming with the first point which we discussed in the previous week as well, we have a uniaxial stress strain relationship for a material like this, in which we consider that both under the tension as well as the compression. So, we can consider that one side of the given system is depicting the tension behavior of the system, whereas the another side is defining the compression in the given system. Now, in general we are considering first that the system has similar behavior in both the tension and compression, which is the typical nature of most of the ductile materials. For materials like concrete, they have a different behavior which is like weaker in tension compared to the compression of the given system. So, accordingly we modify the general relationship of the given system. But now coming to this particular point, what we realize that in a given system for any of the uniaxial cases, the basic utility of the stress strain relationship is to identify the stresses in the form of the strain expressions of the given system, or we can also express it in the opposite manner, that the strains are expressed as a function of the stresses. So, knowing this relationship, the user can track that how the material response changes at the different levels of the strains in the given system, or the user can also track how the material strains appear in the system as the different level of stresses are introduced in the given system. So, based upon the utility, we utilize the both the ways of the expression, where the stresses can be expressed in terms of the general strain relationships, or we can also utilize the strains which are being expressed in terms of the stress at the given system. Now, in the given form we have identified there are one path which is OABC in the given system. So, if you locate the path OABC in the given system, it is considered as a strain hardening material form, in which up to a certain point the material comes to the initial yield of the given system. Up to the initial yield we can consider that the material follows the general Hooke's law, and beyond that the material follows the nonlinear relationship in the stress strain behavior of the given system. At the same time, the strain with the increasing values also leads to the change in the stress or the subsequent increase in the stress values in the given system, and that is how we define that the system has the hardening kind of a behavior in the given system. Such kind of materials can also be idealized with a constant value of the hardening rule in the given system, which means that as the stiffness of the given system continuously changes as we are going with the strain hardening ranges in the given system, the easier approximation can be made in the given system by considering a bilinear kind of a relation, in which up to the yield the material follows the elastic modulus, which is based upon the linear relationship, and beyond the given yield point the material follows a reduced elastic modulus of the given system, and that is the E of t, the overall tangent modulus of the given system. Now, in any general situation, if we are following the path OABC in the given system, the user need to track the elastic modulus or the tangent modulus in the given system at each and every point of the given system. So, with the different values of the strain, the value of the modulus will be defined independently in the given system. Whereas when we come up with the simple OAD profile of the given system, in that we have now only defined the parameters which are identified as sigma y naught, which is the initial yield requirement of the given system, the initial elastic modulus of the given system, the linear elastic modulus, and then the tangent elastic modulus of the given system. So, the dependence of the stress strain relationship or any of these expressions which we are expressing, which we are defining for the given system, reduces from the direct pointwise relationships to a simple 3 parameters of the given system. So, this is how we can make the simplified assumptions in the nonlinear material response of the given system by considering not the overall nonlinear profiles of the given system, but approximating with some of the standard bilinear or the subsequently different kind of profiles in the system, in which the number of parameters can be reduced and they can be defined with more favorable and the simplified number of parameters in the given system. In the similar manner, the user can also come up with a path which is OAE in the given system, and in this situation we realize that the corresponding path between A to E follows a perfect plastic behavior, which means that the tangent stiffness value will be 0 for the given system, and the system will not experience any further increase in the stress as the subsequent strain measures are increasing in the given system. So, with this idea in mind, we realize that there are different ways in which the general material profiles can be adopted, and we typically look for certain number of parameters to define this material rule. As we simplify the relationships, the requirement on the number of parameters can come down with the simplified manner, which can be utilized better in a better manner in the numerical analysis or the analysis of the structural systems. So, with this point we realize that the basic path which the system is following, it could be dependent upon, it could be defined based upon any of these profiles of the given system, and these parameters which are identified for the given system are typically the one which are the characteristic of the given particular path which is defined for the given material rule. Now, as a basic requirement, we have already said that path OAD, which is the simple bilinear profile of the given system, only requires 3 parameters of the given system, whereas path OABC, which is the path required with respect to the general strain hardening, comes up with the continuous evaluation of the E of t in the given system. So, ET value can be evaluated at each and every point of the given system, and that comes out with a more incremental based analysis in the given system. Now, at the same time, the present loading criteria are shown only with one direction of the loading, where we have considered that the system is either loaded in tension or compression in the given system. The moment we go with the unloading profiles in the given system, so just to draw a parameter in the given system, so from the point C, which is say the maximum point up to which we loaded the given system under say tension, now the user starts to unload the given system. So, the system will come down to the undeformed state. It will try to come to the undeformed state with the initial elastic modulus E of the given system, and as we realize that at this given position, when the stress value in the system reduces to 0, system still has some amount of residual strain in the given system. We typically identify that this is the plastic strain which is available in the given problem, and the recovery which has been made in the given system with respect to the total strain, that is equivalent to the elastic strain of the given system. So, we realize that as the unloading is taking place within the tension part of the given system only, the system simply goes with the elastic modulus E, which is already defined in the previous part. But as we move further beyond the tension zone and go with the compression loading on the given system, now the user also need to define that what particular behavior the system follows. So, if you recall the discussion which we did in the last session, we come up with the 2 possible ways in which the system response can be identified. One we define as a kinematic hardening in the given system, and so I will write these values as sigma y1 and sigma y2 in the given system. Of course, these are the negative values because they are appearing with respect to the compression side in the given system, but the utility is that the compression loading on the system can result into the start of the yielding at the lower value compared to the original yield point which has been obtained for the given system. So, if the situation arises in this manner, which we typically describe by the simple behavior that sigma of y naught minus sigma of y minus sigma y naught in the given system. So, if the situation arises in this manner, we typically express that the individual condition, of course this is also with the negative sign. So, we consider that the original value of the yield which was there in the tension of the system has been reduced by certain margin, and that is what is typically the behavior which we see with the kinematic hardening in the given system. Whereas, if the overall system under the compression also goes with the similar behavior and the increase in the, so typically with respect to the loading part which has from which we have started to unload the given material, that also becomes important, that up to what loading path the system has been given the tension load in the given original problem. So, beyond this point if the system comes down, so we can further say that the value over here also increases, and that value is beyond the initial yield strength of the given system. The initial yield which is defined in the tension of the given system, it increases beyond that, and that is how we come up with the solution with the incremental value in the given system. So, this is defined as the general isotropic hardening in the given system. So, in general we consider that the systems which are subjected to any kind of load reversal where the cyclic loadings are provided, the system more or less we assume that follows a isotropic hardening in the given system, which becomes easier to follow. But if there are conditions like due to some kind of dislocations which typically take place in the given system, and due to the anisotropy which typically exists within the material, the system somewhere shows the behavior which is not equally attributed in all the directions of the given system, which means that the behavior of the yield which is there in the system with respect to the tension part will not be reflected in the same amount by in the compression phase of the given system, and that is where the overall net value reduces for the given system. And this typically kinematic hardening can also be followed based upon the particular material behavior. So, here we make this point also clear that the general material rule which we follow in the given system should also be validated with the experiment. So, whether the material is following the isotropic hardening or the kinematic hardening has to be verified with respect to the experimental solutions. Also, the initial point of the yield or the point at which the unloading has been started with the given system, all those sustained parameters has to be tested with the experimental part, and that is where the number of parameters in number of situations are in fact evaluated based upon the experimental observations of the given system. But the point is that as we go with the cyclic loadings, now the number of parameters which we initially define for the system only based upon the tangent modulus of the elasticity increases, and they also now include that what kind of hardening behavior the material is following, whether it is a kinematic hardening or isotropic hardening. It also understands now that up to what level the system has been loaded in say one of the parameter from which it starts the load reversal. So, these are the parameters which also now get included in the general behavior of the given system. Now, we will try to come up with some simplified relationships which are defined for the materials which are showing the strain hardening in the given system. We will try to follow it for both the cases where the nonlinear hardening is adopted, and as well as the linear hardening case we will try to define as a special case of the given system. So, if we realize that at the beginning of a given system there is a material which, so this is the stress strain profile which we have drawn for a given system. With the initial elastic modulus E, the system goes up to a certain value, say the yield somewhere appears over here. So, we are doing this process much above the yield point already, which is in the nonlinear range, and at this point the user can define a tangent to define the particular value of the tangent modulus of the given system. So, at the specific point where the user is looking to define the value of the or where the parameter is being evaluated, the tangent modulus can be drawn, which is the slope on the given curve, and this value of the tangent modulus once known to the user can identify that any part of the small increment in the stress parameter, which is d sigma, can be provided, and corresponding to that the change in the strain parameter can be evaluated for the given system. So, if you just show it in this manner, so this is the tangent modulus corresponding to which the user has evaluated the different point in the given system, and this becomes the specific value of the epsilon n in the given system, and this is the load increment in the given system. So, if I define it in the equal manner, so this is d sigma and this is d epsilon in the given system. So, change in the stress increment leads to the change in the strain of the given system as well, and that has been defined with respect to a fixed point on which we define the tangent modulus, and we give this relationship using this parameter of the given system. Of course, later we will see that we require certain corrections also in the given system, but as a first part of the given analysis, we realize that now as we see the given system from this point which is located over here, the user can unload the given system as well. So, if I just define the system. So, if the unloading takes place from this given system, from the point where the initial point has been located with the constant tangent modulus of value E t, the system will come down with the elastic modulus, which is the initial elastic modulus of the given system, and it will somewhere be located at this particular point of the given system. Now, we can break the given system into two parts, which are the corresponding elastic increment in the given system, and the remaining part will be the plastic increment in the given system. So, knowing these two increments in the given system now gives the user a possibility that these two parts can be individually characterized in the given system. So, out of the total strain parameter which is evaluated, or the total strain increment of the given system, now there is a possibility that the user can subdivide the portion of the plastic strain and the elastic strain from the given system. Of course, this is happening with respect to the conceptual understanding of the given system. The physical system may be subjected to the strains where the transition from the elastic to the plastic strain will take with the different members in a different situations, but at a general condition, once we know the given overall strain in the system, and by knowing the stress level on the given system, the user has a possibility to break down these two the overall strain parameter into the plastic and the elastic strain components of the given system. So, if we look at the given system, we realize that the elastic strain in the given system can be defined as the increment which is defined for the given system, which is say d sigma, divided by E, which is the elastic modulus for the initial constant linear elastic properties of the given system. Once we know this parameter of the given system, the user can come up with the plastic strain on the given system, and that can be defined as d of epsilon, which is the total strain of the system minus the elastic parameter of the given system, and now this can be written as d epsilon minus d sigma upon E in the given system. Now, we can change the given parameter of the d sigma in terms of the strain parameter, so that we can take the common d epsilon parameter of the given system, which is equal like saying that I can try to express the elastic and the plastic component of the strain in terms of the overall strain representation of the given system. So, if we do it in this manner, we realize that the d sigma, which is identified over here, can also be defined in terms of d epsilon with the standard relationship which we have already written over here. So, utilizing this relationship, we can write it as d of epsilon E, which is the elastic strain component, is equal to E t upon E into d epsilon. Similarly, the user can now also define the plastic strain component with a similar profile, and if I take the d epsilon common from the given system, it becomes 1 minus E t upon E in the given system, and this can be simplified as E t c times d epsilon in the given problem. So, the ratio of E t upon E when subtracted with the 1 parameter, that typically gives us the parameter which we define as a C, and that typically now describes the plastic strain parameter in the given system in terms of the overall strain increment in the given problem. Now, knowing this parameter, what we also realize that the user can now go back and try to convert the given value of the overall strain in terms of the stress increment of the given system, so that the initial idea of the plastic strain, which is located by this value, can also be reflected with respect to the stress increment of the given system and the corresponding slope which will be represented for only the plastic strain component of the given system. Again, to modify this part, that this is not what physically is taking place in the given system, but as a concept, at a conceptual part, we are trying to break the system into the elastic and the plastic strain components. We are defining the elastic component with respect to the elastic modulus, which is E for the given system, and then we are also trying to come up with a modulus which will describe the plastic strain exclusively in the given system in terms of the stress increment of the given problem. So, if we do that, we realize that the expression which is written over here, we can come up with the same d of epsilon p is equal to 1 minus E t upon E, and we can write this as d of epsilon, which is known to us now in terms of the d sigma expression. So, utilizing this expression, it gives us d sigma upon E t in the given problem, and if we just modify the expression, it gives us 1 minus 1 upon E t 1 upon E into d epsilon. So, we realize that now this is the expression which typically can be identified as the effective modulus, which is representing the relationship between the plastic strain and the overall strain increment in the given system. So, we will just see that how this overall expression can be modified in the given system. So, using the same idea, we just try to show that the overall strain component has been broken into two parts, the plastic and the elastic component of the given system, and then we are able to express the plastic strain component in terms of the overall strain with a parameter of the C, which is 1 minus E t upon E in the given system. We must also realize that in most of the situation, as the system undergoes the nonlinear stress strain relationship, the tangent modulus, which is defined for the nonlinear case, will be lesser than the initial elastic modulus of the given system. So, as the material deforms nonlinearly, the elastic modulus of the given system reduces corresponding to the initial elastic modulus of the given system. So, that is where this given value E t upon E will always be coming out to be lesser than 1. Now, in this similar manner, we did the next part where we express the system in terms of the sigma component, and by doing that we got to know that this is the expression which can be written, and by expressing the given system in this manner, we are somewhere able to define this modulus which is identified as h in the given system, and now it can be written that the given modulus h typically gives the relationship between the sigma component, which is the increment in the given stress parameter, and the plastic strain parameter of the given system. So, the user can write this expression also as d sigma equal to h times d of epsilon p, and the h parameter has been identified as E t upon E t into E divided by E minus E t in the given system. And now, this parameter is effectively defined for any part of the stress strain relationship where the parameter of the stress increment has been defined with respect to the identification of the plastic strain parameter in the given system. Now, coming with the specific case where the user is having the constant value, or sorry, the 0 value of the E t, which means the perfectly plastic case, we will realize that the E t value will be coming out to be 0 in the given case, and the overall h value will also come out to be 0. Now, looking at this expression, the value which we have defined over here does not make much more sense now, because reducing the value of h 0 in the denominator will make this expression not probable, because somewhere the overall term of the epsilon p will come out to be infinite in the given system. Whereas, what we realize that the given system, once it is subjected to a perfectly plastic state, any of the stress increment in the given system is absent. So, ideally it is the d sigma which is absent in the given system. So, whatever deformation the system is undergoing, that is purely plastic with respect to the given system. So, at any point the system will just come down to the original condition, and the overall strain which the system has obtained for corresponding to those changes can be simply defined as the plastic strain of the given system. So, with this parameter we realize that there are some standard relationships which we can define for the general stress strain relationship, which are in terms of the nonlinear material rule. And now, utilizing these relationships, we can go ahead with formulating the regular problems in which the structural systems are considered, and we define the overall stiffness parameters of the given system. So, this parameter can be finally written with respect to these final relationships, which is d sigma is equal to d epsilon plus d epsilon p, which is the total strain component is broken into two parts. Then the d sigma is identified with respect to the elastic component. Similarly, the d sigma can also be defined with respect to the plastic component by the second rule, which we have defined, that d sigma is equal to h times d epsilon p in the given system. Now, what we can also do, we can express this expression in a little alternate form, in which we write the elastic expression as a total strain minus the plastic strain component of the given system. And what we realize that d sigma, as the stress increment is defined in the given system, it is defined as that the increase in the plastic strain parameter of the given system will lead to the decrease in the overall stress increment of the given system. So, this also comes down to the same point that if the overall strain in the system is same as the plastic strain of the given system, the increment in the given system with respect to the stresses will become 0. That means, the perfectly plastic material which is subjected to the behavior like that will be having no amount of stress increment in the given system, because system cannot take any further amount of stress beyond the yield, and in this situation all the strain which the system is subjected to will be purely a plastic strain for the given system. So, with this idea we stop over here. We have identified the basic relationships for the given system, and now we will try to utilize them in the subsequent session for the total member components. Thank you everyone.